S1. Let's let NB equal 8. For this example, I'm going to introduce to you a modulation scheme called polar non-return to 0. And that's basically a fancy term. The non-return to 0, sometimes we call it polar NRZ. It's a fancy way of saying the following. S0, okay, is equal to plus 1 at sample instance 1, 2, and so on up to NB, and 0 elsewhere. Okay, so that's cool. Our signal has a duration of exactly NB samples. And S1, okay, is equal to this. Oops. In fact, I think I presented this example already. -1. Sample is 1, 2, and so on up to NB is equal to -1 and 0 elsewhere. So if I was going to modulate this vector Bj, this is what it would look like. Okay, so for the first NB samples, this 0 becomes S0, okay. And that's a 0, so S0 8 positive going samples like this. The next 8 I have a 1, so I replace that with S1, okay. And this is NB plus 1, NB plus 2, up to 2NB. Then the next one is again a 1, so I replace that with S1. And I get an additional 8 samples of S1. From 2NB plus 1 to 3NB. Then I have a 0. Additional 8 samples. From 3NB plus 1 to 4NB. And finally I have 1. Final 8 samples like so. Up to 5NB. So there is your modulated signal. So the first bit maps here, second bit maps here, third bit maps here, fourth bit maps here, and the fifth bit maps here. And then once we go through, again, we're mostly dealing with discrete time in this course, but once that goes through a digital to analog converter, the signal would look like a series of square pulses. Okay. Where here I'm setting it at 0, 1, 1, 0, 1. Okay, here's another example. So this is a famous type of signaling, polar NRZ. It's called non-return to zero because we only cross zero, we never end up at zero. So the value of the function is always either +1 or -1. It's never zero. Okay, another type of modulation that we're going to hear a lot about. Called binary phase shift keying. Or BPSK. BPSK, what I have is S0 is equal to sine of 2 pi k over NB, or 1 for k equal to 1 through NB, and 0 otherwise. S1 is equal to sine 2 pi k over NB plus pi. From 1 to NB and 0 otherwise. Okay, this is why we call it binary phase shift key. Because there's a phase shift of pi between S0 and S1. But we can actually represent this a little more succinctly. What does a phase shift of pi mean for a sinusoid?
Cosine.
That's actually pi over 2.
Oh.
For pi,
Minus sign.
it's -1. That's right. So in fact, this is equal to minus sine 2 pi k over NB. And so therefore, this is equal to minus S0k. We'll deal with this a little bit later, but these signals that are antipodal like this, where we have S0 and S1 equals minus S0, these types of signals are very efficient in terms of noise, in terms of transmitted energy. So let's sketch S0. Does everybody have S1?
Yep. Oh, S. S0.
Everybody has S1?
I'm just writing S1 now.
Okay, let's illustrate S0.